presenting here the following slideshow, titled Going Out with a Bang, Resonance Energy of Benzene Determination. This presentation focuses around the Physical Chemistry 1 lab experiment titled calorimetry, and is divided into 4 sections: the introduction, theory, results, and discussion. An important question to ask is why benzene? Benzene is an extremely important molecule in organic chemistry. It is the focus of a number of lectures in Organic Chemistry 1 and 2 due to its unique properties. Benzene is also an additive to fuels, as well as used in the synthesis of many organic compounds. Benzene is unique because it is resonance stabilized. This extra stability is contributed to its conjugated structure, in which there are 3 pi bonds. These pi bonds are delocalized around the molecule, providing it the extra stability. This extra stability is the focus of this lab, and the determination of how much extra it is stabilized is the end goal. The figure at the bottom of the screen is a Segrest-generated image of a benzene molecule. The reaction of benzene and cyclohexane produces a molecule called CDDT. This reaction is isodesmic, meaning that the number and types of bonds stay the same from the products to the reactants. This reaction scheme can be seen at the bottom of the slide and is crucial to understanding the theory behind the experiment. Using the calorimeter seen on the bottom left of the screen, the heat evolved during the combustion of cyclohexane and CDDT can be used to determine the resonance energy of a benzene molecule. Prior to the lab, I hypothesized that the combustion of CDDT would release more energy than the combustion of cyclohexane. This is due to CDDT having more bonds than cyclohexane. The bond energy is released during combustion, so a greater number of bonds means more energy. Additionally, I hypothesized that the total energy values will be more negative than the heat of combustion values. This is due to the fact that the changes in moles of gas is negative. This means that the second term in the calculation of the heat of combustion will be negative and subtract from the total energy value. This equation and more detail on the theory will be seen in the following slides. The bomb calorimeter is at the center of this experiment. In the instrument, the volume is held constant while oxygen is pumped into the system. The result is an oxygen-rich environment at high pressures. With the sample molecule inside, a fused source vaporizes the sample and ignites a combustion reaction. In the gas phase, one might assume that the sum of the heats of combustion of benzene and cyclohexane would equal that of CDDT. This assumption neglects some important chemical characteristics, however. First, benzene is a conjugated molecule. This causes additional stability compared to that of cyclohexane and CDDT. This stability is the resonance energy mentioned earlier. Thus, the difference between the enthalpy of combustion for benzene plus cyclohexane and CDDT is the resonance energy. Another important factor that influences the final result is enthalpy of vaporization. The sample molecules are all analyzed in liquid form. During combustion, the molecule is vaporized. Because each molecule has a different enthalpy of vaporization, this needs to be included in the data analysis as well. At the bottom of the screen, an equation taken from the lab manual shows how everything comes together to give the resonance energy. Procedure and data analysis will determine the values for D and E in the image. Due to the toxicity of benzene, the enthalpy of combustion will be taken from an outside source along with the vaporization values. The following slides will go through the results. On this slide, graphs of the data from the thermometer in the instrument can be seen. Time in seconds is plotted on the x-axis, with temperature in Celsius on the y-axis. Each graph has 5 labels placed on them. These points are used to calculate the temperature change during combustion. TI represents the point at 60 seconds after the readings begin. TA is the moment just before the bomb goes off. TB is the point at which the system has undergone 60% of its total energy change. TC is the maximum temperature reached, and TF is 90 seconds after the maximum temperature reading. At the bottom of the slide, equation 1 shows how these points come together to give the temperature change during the run, with R1 and R2 representing the slopes between points TI and TA and points TC and TF respectively. The calculated results are on the next slide. Table 1 holds the obtained literature values for the variables required to calculate the resonance energy. Their corresponding sources are listed at the bottom of the slide. In Table 2, the temperature change calculated from equation 1 is listed for each run. As can be seen from the data, runs 1 and 2 of cyclohexane provided similar results as did runs 1 and 2 for CDDT. A sample calculation of CDDT run 2 with steps is provided below Table 2 for reference. Table 3 lists the calculated total energy represented by the symbol delta U. It is calculated using equation 2 underneath the table. The term C-bomb is the heat capacity of the calorimeter. This value was provided before the experiment using a benzoic acid standard to save time. Again, a sample calculation for CDDT run 1 can be found at the bottom of the slide. Additional steps are taken in the sample calculation to account for the portion of the fuse that burns and gives off energy at 9.62 joules per centimeter. The final calculation is presented in kilojoules per mole. Table 4 provides the final enthalpy of combustion values for each run that this lab set out to determine. Those values are averaged to get the results in Table 5. Delta U is converted to delta H using equation 3. A sample calculation for cyclohexane run 1 is provided as well. Equation 4 is the final calculation needed to obtain the resonance energy value for benzene. All of the variables are substituted in to obtain a final value of 234.95 kilojoules per mole for the resonance energy of benzene. First, we must revisit the two hypotheses presented before the experiment. The first hypothesis proposed that more energy would be released in the combustion of CDDT than that of cyclohexane. This turned out to be true, as the change in enthalpy for CDDT was negative 7,464.4 kilojoules per mole versus negative 3,957.4 kilojoules per mole for cyclohexane. The second hypothesis stated that the enthalpy of combustion will be more negative than the total energy value. This also turned out to be true for all 4 sample runs. As a whole, the experiment ran smoothly, with no reported problems from those involved with acquiring the data. The final result of 235.95 kilojoules per mole was significantly higher than results found from an online source, which stated the resonance energy of benzene was around 150 kilojoules per mole. There were some drawbacks to this experiment. First, the values for C-bomb and enthalpy of combustion for the gel were provided to students rather than acquired the same day in lab. This was done in the interest of time, but slightly different constant values may have been attained if the constants were calculated on the specific day the experiments were run due to external conditions changing. Additionally, time only permitted for 2 sample runs to be taken of cyclohexane and CDDT. Calorimetry has additional usage based on what I learned performing this lab. One of them would be the determination of vaporization energies. An additional method of determining resonance energy would be using computer modeling programs like Cygress, where all the relevant variables could be determined. Just a few acknowledgements are needed to wrap up this presentation. First, thank you to Dr. Wagner, who performed the experiment, acquired all the data, and recorded himself doing so that we could watch and actually make this lab possible. Our TA Paige, who was helpful throughout and was able to answer questions for us, and the University of Pittsburgh for providing the resources to do this lab. Thank you for listening.